Hey y'all, okay, so I'm going to explain how to do some of the static equilibrium problems. So how you get to it is you go to Blackboard, and then you go to the class examples folder, and then all the way down at the end, click on static equilibrium examples, and then I'll go through these with you. So I'm just going to do one video per example, so I can kind of space it up and you have time to like work it out before you see the next one. Okay, so this is the first one. So basically, if there would be a picture, like he would draw a picture so you would understand like there's a kid sitting here and a kid sitting here and the seesaw is on a little axis. Like here, I'll draw the picture for you. So I mean, if you don't have the picture, it kind of doesn't make sense why there's like weights coming down. But so this is what the seesaw looks like, okay? Free body diagrams, though, when you draw them, they can't be connected to anything. So the seesaw is the object that we're looking at. It can't be connected to the little human kid sitting right there, and it can't be connected to the little thing that makes it pivot. So that's why he just drew the line. Okay, but it kind of makes sense when you look at that, like where all the forces are coming from. Okay, so this is the free body diagram. The pivot point, so it's this bar right here, the seesaw is sitting on something, right? Whenever you sit on something, you have an opposite force, right? So that's where the normal force is coming from. Also, you have the weight of the seesaw. You always put the weight of the seesaw in the center of mass, and obviously this is a uniform seesaw, so this would be the center of mass. And so it gives you that the mass of the seesaw is 4 kilograms, so just 4 times gravity. Make sure you know G isn't like grams or anything. G stands for gravity in these problems, so don't get that mixed up. It gives you, it's 25 or 2.5 meters from the center of the seesaw to kid A. And then it gives you that kid A weighs 30 kilograms, or is 30 kilograms of mass, so 30 times G would be its weight. And then it doesn't give you X. It doesn't give you the distance between the center of mass and, or the pivot point and kid B. And so we're trying to find X and we're trying to find the normal force. So whenever you draw the free body diagram, just make sure you don't include it like touching anything, so it wouldn't be touching the kids or the little pivot point thing here. And then make sure you do the axis. So obviously we're used to doing the positive X and the positive Y, but make sure you draw the torque. Going counterclockwise is always positive. Okay, so when you set it up, obviously like for this quiz, and I guess on the test, if you see a static equilibrium problem, just go ahead and draw this chart thing, so X, Y, and Z. Z stands for angular motion, so anything that's going to make it rotate, basically. So just draw the chart, and in each little column, do the sum of the forces in the X direction equals 0, Y, and the torques equal 0. Why is this? If an object's in static equilibrium, then there's no net forces acting on it in any way. So there's no net forces acting on it in the X direction, making it move up or down, in the Y, making it move from side, and then not in the, I guess Z is angular, but it's not rotating. Okay, so we just know that it's in static equilibrium, it's not moving. You always have to pick the center of mass, or you're always trying to pick the pivot point at a place where it will eliminate most of the unknowns. So we picked, I know it says right here, but we picked the center of mass for the pivot point on this one. But if you look at all of your forces, you can be like, okay, well right here, I don't know the normal force right here. So it would be beneficial for me to pick the pivot point where the normal force is coming out, because when you have torque, there are no torques applied to the pivot point, because it's like, if you have a pencil right here and it's like sitting on my finger, if you were to like press on the pivot point right here, I could press as hard as I want, but it's not going to make it rotate. However, if I were to press on either side, it's going to make it rotate, right? So the forces on the pivot point in the middle, they aren't included in the torque calculations. So basically, to make it easier on yourself, just pick the place where there's the most unknown forces coming out of that place, if that makes sense. So whenever you're calculating torque, remember the formula is RF sine theta. And for all of these, sine theta is sine of 90 degrees because it's the angle between the force and the object. And this is 90 degrees for every single one of them. So sine of 90 is 0 or is 1. So we just disregard that. So basically, we're just doing RF of kid A and then RF for kid B. And we're adding that, and we know it equals 0 because it's not rotating, right? So basically, let's look at which one did he do first? He did kid A first. So for kid A, R, so what is R again? R is the distance between the pivot point and the place where the force is being applied, so in this case, the kid. I know what you're thinking. It looks like it's going in the negative x direction, so why isn't it negative? Well, remember, R is a radius. Radius aren't vectors. So if you have a circle, you could have a radius right here, and it's like, 3 meters or something. It wouldn't be negative 3 meters, right? Like, it's a magnitude. It's a, like, because you could turn the circle, right? And it could just as easily be over here, the radius, right? So whenever you're looking at R values, never make them negative, even if they seem to be going, in the negative direction. Okay, so for this one, the R value is 2.5, and then it's RF, and then the force is the weight, which would be 30 times 9.8. And he just leaves the G variable in. You could multiply it out before, but he just sticks in the G at the very end, but it doesn't really matter. Okay, and so the plus and negative sign. So the plus, if you're looking at kid A, so if you just think about the seesaw like sitting right here, and there were no kids on it, okay? You can tell which way it's going if you imagine the kid sitting down, just one of them. So like for kid A, this is the seesaw. If kid A were to sit down on the left of my pencil, the pencil would, or the seesaw would rotate this way, right? So that would be a counterclockwise rotation, which is positive as we defined. So that's why there's a plus right here. Okay, and then we'll do our kid B. So kid B, we don't know the R value. That's what one of the things we're trying to solve is X. So R, and then F is 25 times 9.8, or G, equals 0, because the torque equals 0, we're not moving. And then it's negative in this case because, again, if you just imagine the seesaw just sitting here and kid B sat down, it would tilt this way, right? Which is clockwise, and that would be a negative direction for us. So that's why it's negative. And then equals 0. And then from there, it's just simple algebra. He did 2.5 times 30G minus, he really didn't do anything different between these two things. He just solved for X, and then you got 3 meters. That's pretty simple, guys. And then, okay, so that gave us our X value. We're still trying to find our normal force. And so we're looking at our 3 columns. Well, there's no values in the X direction, or there's no forces in the X direction, right? We're just all going up and down, and then we have torques that will rotate it. So if you want, you can make like a huge X through your X direction column. So we started with our torque. I would recommend always starting with torque, because the torque, you get some of your forces canceled out. Like, does that make sense? Like for our torque, we didn't even consider the normal force. So for the Y, we would have to consider like the normal force just by itself, but here we don't even have to consider it. So if you start with torque, then you can solve for something without having to worry about the other missing variable. So yeah, just start with torque. And then, so for a Y, this is easy. They all add up to 0, right? Because it's not, if the N was greater than all of these, then it would, it would start flying, or it would go into the ground. So we know that it's balanced because it's not moving up or down. So we know that 30G, it kind of is weird, but so we know that N equals 30G plus 4G plus 25G, right? Because they're balanced. And then, so like this, N equals 30G plus 4G plus 5G. You just subtract them all to put them all on one side to set it equal to 0. That's where he got this from. Okay, so N minus 30G minus 4G minus 25G all equals 0. You just combine the variables, and like I said, he plugs in 9.8 at the end, I guess, to make it easier. So like, G is, think of it like an X or a Y or any other variable. You can add like variables. So you add them all together, you get 59. Then you plug in the 9.8. And then when you solve it, it gets 578 newtons. Okay, I hope that helps.